So let's continue our workshop today, and our next speaker is Federico Cipolletta, I hope it's pronounced correctly, who will tell us about Spritz for general relativistic magnetohydrodynamics with neutrinos. So please go ahead, Federico.
Thank you. Hello, everyone. I'm Federico Cipolletta. I'm currently a research fellow at the Leonardo Corporate Laboratories at Genova in Italy. And I will present the code that we developed together with Bruno Giacomazzo, Riccardo Ciolfi, Jay Carinani, Lorenzo Enoggi, and several former master students of Bruno, Lorenzo Sala, Edoardo Giangardi, and Beatrice Giudici. And then it's currently continued to being developed within the TCAN collaboration by Lorenzo Enoggi. So if you have any question, you can reach me at my personal email address, that is this one. And you can visit also the website for the TCAN collaboration if you are interested in such a work. So just to start with the Spritz, we published our first paper in 2020. Here we presented the implementation that we done inside this code, which was an old project by Bruno. Starting from Whiskey MHD, we implemented the staggered vector potential evolution for modeling the evolution of the magnetic field. And this panel gives you an hint of the reason for that, because if you this is a result from the Balsara 1 shock tube test, the result for the Y component of the magnetic field. Those are the Balsara tests are shock tube tests, so they are in 1D. But you can see that if you adopt self-centered vector potential formulation that is represented by the blue dot, you can get some post-shock oscillation that are constant and does not increase with time, but can create several problems during more complex evolution in 2D or 3D. While when you use a staggered vector potential formulation that is represented with the red diamonds, you can just get rid of those oscillations. In Spritz, we also, in the first version, we implemented also the several reconstruction order. We have the second order min mod, third order PPM, and recently in our recent paper, we also implemented the WinOZ fifth order method with the work by Beatrice Giudici. We also adopted the treatment for the equation of state through the EOS Omni Thorn, that is a thorn that is publicly available within the Einstein toolkit. And allows for a general treatment of the equation of state. We performed several testing in 1D, 2D, and 3D, and we showed second order convergence in general. So the staggered vector potential, for those who are new about that, is sketched here. So you can see that here there is a cube representing one grid cell of your numerical simulation. And usually the self-centered version of codes consider all the variables in the center of the cell, so in the point Pijk here. While when you consider when you want to stagger the vector potential, you should consider the vector potential to be placed at the edges of the cell and the magnetic field to be placed at the center of the faces of the cell. So here you have a table that gives you a summary of the location of the different variables in the grid points. And you want to adopt such a formulation for the vector potential because thanks to this relation, you can obtain the divergence-free condition on the on the magnetic field to be automatically satisfied. Here in the Spritz code, we also implemented the different order of reconstruction methods, because when you perform a numerical simulation, usually you may want to have some control on the reconstruction method that you adopt. So in general, adopting lower order gives you more dissipation. But this is a problem because lower order means that your solution is less accurate. Okay, you have less information about the results. And here we have a test that we presented in the first paper showing the results of a spherical explosion test. This is a very engaging test in 3D that consider a high density sphere that is exploding in a low density surrounding. And so without magnetic field, you have at the end you have a perfect sphere, let's say. But with the presence of a Z component for the magnetic field, the explosion tends to follow the lines of the magnetic field. And you can see that this test is really engaging for when you adopt Cartesian coordinates. Indeed, here at the diagonal, you have some spurious accumulation in the Lorentz factor. Anyway, adopting the mean mode, so the second order, we were able to perform this test, also adopting a medium magnetic field magnitude. For what concerns the equation of state, we would like, when starting developing Spritz, we wanted to insert to let the user have the possibility of adopting any kind of equation of state. So you have the possibility of adopting analytical equation of state of the type of the ideal fluid, or of the polytropic type equation of state. And these kinds of equation of state are guaranteed by the Einstein toolkit EOS Omni that provides you support for every kind of equation of state. In addition, EOS Omni provides also the support for tabulated equation of state, and that is what we implemented and we showed in our last paper about Spritz. So when you want to adopt a tabulated equation of state, you should consider an equation of state of this kind. This form is from the Compose website. So you have the pressure that is dependent on the rest mass, the temperature, and the electron fraction. But in order to effectively adopt a treatment for such equation of state, you should put some ingredients in. So you need at first to select one initial slice for the equation of state, and we in our implementation we let the user to choose between constant temperature or constant entropy slices for the initial data only. So the table dimension is reduced to 2D. Then you need also to add to use a code for reading the initial data and for producing the initial data, and we decided to adopt Lorin. You should also impose another condition in order to make this table reduced to 1D, let's say. So you have the pressure that is only dependent on one variable, and you can, for example, choose to set the Bethe equilibrium. And you also should provide some support for the evolving temperature and entropy and the electron fraction within the contour prime, and we adopted the Palenzuela 1D method. And in addition, we also provided a modification of the public Zelmani-Lick thorn that can be found in the Stellar Collapse website in order to work with Spritz. in order to model the neutrino emission and absorption. Stepping into the Zelmani-Leak code, the dominant process for neutrino leakage are those processes here. So you have electron capture, positron capture, pair annihilation, and plasmon decay, and all those processes produces neutrinos. Okay. The fundamental quantity that you should use to model the neutrino emission and absorption is the optical depth. That in the isotropic neutrino radiation can be written as this integral here. And then you have to consider two regimes for the neutrinos. One is the absorption regime for high density, density higher than 10 to the 12 gram per centimeter to the -3. And here you have to consider some reaction that are source of opacity. So the scattering on neutrinos on nucleons, on nuclei, and the absorption of neutrinos and antineutrinos. And for all these reaction, the Zelmani-Leak code can provide you with an estimation for the cross section of those reactions, and with that you can obtain the opacity, the number rate, the energy rate, and basically the energy associated with a particular kind of neutrinos. And all those quantities here depends on the temperature. So evolving temperature is fundamental for this model. And then you have also the free streaming regime. So the regime in which the neutrinos are emitted, when the rest mass density is less than 10 to the 12 gram per centimeter to the -3. And in this case, the Zelmani-Leak considered all those reactions together with the Bremsstrahlung, and gives an estimation for the number rate and energy rate for such processes. And again, those quantities depends on the temperature more than linearly. And these give you an hint that constraining the temperature can avoid issues at the neutron star surface where you have a big jump in the temperature. Okay, so because you have the surface of the neutron star surrounded by an atmosphere that is in general considered to be at zero temperature or temperature lower than the one at the neutron star surface. In addition, the Zelmani code allows you to model also the reheating, so the reabsorption of neutrino that produce heating, and this modifies basically the luminosity associated with neutrinos. The effective rates, number rates of neutrinos is modified by the neutrinos being reabsorbed. So considering heating alters the luminosity of neutrinos. In addition, the Zelmani-Leak code deals with the pressure. So in the absorption regime, the neutrino pressure is added to the source term. The Zelmani-Leak code has a ray-by-ray approach. So when you start from Cartesian coordinates, you interpolate the quantities in spherical coordinates and then interpolate back to the spherical coordinates. And he operates in an operator split manner. So the electron fraction and energy density are updated at each time step. So you should care about that. In the paper of 2021, we presented several tests of evolution of a single TOV star, where we would like to show that the implementation we performed of the treatment of tabulated equation of state and the treatment of modeling of neutrinos was good. So we performed several tests, repeating some of those also with GRHydro code, that is a GRMHD code in the Einstein toolkit. And we considered some simulation in octant symmetry, some simulation in full 3D. In particular, the magnetized simulation, those one, were all in full 3D because the staggered vector potential formulation was not supported for octant symmetry. We consider different conditions for the beta equilibrium. We considered or not the temperature evolution, and we also allows the user to switch on the temperature evolution after some time. And now you will see why. And in addition, we perform the same simulation, maybe with and without the neutrino leakage activated. And we also provide the option of activating the neutrino leakage after some time. So for what concerns the results of such TOV simulation, we adopted the LS220 equation of state, tabulated equation of state. We adopted 5 refinement levels with the finest refinement levels with a resolution of 0.12. That means 60 points per neutron star radius, so a resolution of 120 meters in the neutron star interior. And we perform evolution for about 6 milliseconds. This choice was due to limited resources that we had at the time. As I said, we consider or not consider the heating. And we analyzed the evolution of rest mass density, of temperature, of the maximum of the magnetic field, and of the luminosity of neutrinos. So one note about the maximum temperature, with dependence on what you choose as initial data. So with constant entropy or constant temperature, the temperature distribution across the neutron star is different. So when you consider constant entropy, you have the maximum of the temperature that falls inside the neutron star at the center, ideally, of the neutron star. While when you consider an initial data with constant temperature, the maximum of the temperature is at the surface of the neutron star. So between those two choices, there is an important difference to care about. And in addition, the constant temperature evolution are usually the most delicate one, because you have a big jump here from the neutron star surface and the atmosphere. For what concerns the results, here are 2 plots for the runs without magnetic field and constant entropy initial data without leakage. You can see that the maximum rest mass and the rest mass density, the maximum rest mass density and the maximum temperature evolution looks fine between the models. And we also compared the red, solid red, dotted blue, and solid black curve with the same evolution of GRHydro, that is the green one, the dashed green one. And all the results seems to agree perfectly. We have some differences in the temperature here from between Spritz and GRHydro in the maximum temperature, but those differences are really, really small. So it seems to be, those results seems to be validated. In this case, where you have constant. We also consider the same simulation, but with neutrino leakage, and you can see switching from here to here that the evolution is not affected by switching on the neutrino leakage. We also consider the results for the luminosity of different kind of neutrinos. We have the electron neutrinos, the electron antineutrinos, and the other kind of neutrinos all grouped together, and we call that nu-X. And we can see how the evolution of the luminosity as observed at infinity is outputted by the code. We compared the results of the different kind of luminosity between Spritz and Generali, and again we see good agreement in the results. In addition, as the luminosity of antineutrinos is the smallest one, we ended up saying that the electron capture seemed to be the dominant process, because this is the one. Okay. Anyway, then moving forward, we have also the results for the constant temperature initial data without leakage. Here the evolution is different. We see that in every simulation we have a big transient initially, a big oscillation in the rest mass that is then damped down. And we also perform one of those simulations, that is the blue dotted one, switching on the temperature evolution after 2 milliseconds. In fact, you can see that here in the rest mass, the neutron star undergoes a big shock in the maximum rest mass, and also you can see that clearly in the temperature evolution when where you have this big jump initially. Considering the constant temperature initial data is delicate, because you have to choose the initial value of the temperature in a good way. So if you consider a value of the temperature that is near 0, you can see that the evolution of the temperature the temperature has a big increase initially, and this can create problems when you have in simulation. This is the pure hydro case, so only hydro without magnetic field. This is the pure hydro with magnetic field, where in both cases we chose to switch on the temperature evolution after 2 milliseconds. The red one is without, sorry, the red one is without magnetic field, so it is the pure hydro. While the red dashed one is the one with magnetic field, and you can see that the rest mass and the temperature are not affected by the evolution of the magnetic field. And here we have the hydro results with constant temperature initial data with neutrino leakage. Here we switched on the neutrino leakage after a fixed time. So for the blue curve was switched on after 1 millisecond, for the dashed red after 3 milliseconds, and for the black dotted after 3 milliseconds. And you can see that switching on the neutrino leakage does not affect the rest mass and temperature, because those plots are really similar to the one that I showed before. We also noticed we also analyzed the the luminosity of the neutrinos for the different kinds of neutrinos. And you can see here clearly that the leakage scheme is activated in the blue curve after 1 millisecond, and in the other curves after 3 milliseconds, sorry. And again, the electron capture seems the dominant process. And here, as I said, the delayed leakage activation is evident. We also showed a couple of plots for the magnetic field. This is with constant entropy, and this is with constant temperature, with temperature activation after some time, after 2 milliseconds, if I'm not wrong. And here in the black curve, we have also the activation of the leakage after 3 milliseconds. And in the leakage activation, so does not alter neither the maximum magnetic field evolution. Those are other results for the neutrino luminosities, comparing simulation without the reabsorption of neutrinos, so without heating, that is the blue curve, and with the reabsorption of neutrinos, so with the heating in the dashed red curve. As you can see, when you consider reabsorption, when you not, sorry, it is the opposite. So red is without heating and blue is with heating. So when you don't consider heating, you have higher values of luminosity, but this is intuitive in the sense that the neutrinos are reabsorbed, so they are not emitted. Those are the results for the constant entropy, and those are the results for the constant temperature. Here in the blue curve, we have an activation of the neutrino leakage after 1 millisecond. So you can see that the heating affects considerably the neutrino luminosity, so the neutrino emission, luminosity observed at infinity, and the heating also affect, and the heating also needs to be treated with care, because you can have problems with your simulation. Then in 2020, last year, I went to, as a postdoc at the TCAN, and I ported the Spritz code in the TCAN collaboration. So the TCAN collaboration is a big collaboration between several universities with the goal of performing long-term binary neutron star simulation. With the purpose, with the objectives of considering dynamical GRMHD, nuclear and neutrino physics, so tabulated equation of state, neutrino and photon transport, and our processes, in order to, at some point, be able to also model our processes and nucleosynthesis coming out from the simulation. The idea at the base of the collaboration is to take advantage of the strength of each code. So in general, in ideal absence of symmetry, we want to use the Cartesian coordinates, while in the case of axial symmetry, we would rather use spherical coordinates. This is a snapshot from one of the first handoff that was performed from a Cartesian coordinates code to a spherical coordinates code, and was performed by Federico Armengol Lopez. Yes, initially in the collaboration we simulated the disk, so ending off the data from results of a disk in Cartesian coordinates to spherical. And then we started also simulating binary neutron star merger and handing off those data. This is an example of such an off of data. This is a simulation of the missing link in pure hydro, binary neutron star merger, that was performed with Spritz so without magnetic field, and then ended off to ARM3D, that is a spherical coordinate code. And you can see that the disk after black hole formation remains stable and can be continued for really long time. Those images were produced by Federico Armengol. We also have here some images showing the first test that we performed of binary neutron star merger adopting tabulated equation of state. Those are tests in low resolution with finest resolution of 0.24. Those tests were performed by Lorenzo Enoggi when he was a master student of Bruno at the University of Milano Bicocca. In the top panel, you have the equal mass case for the binary, and you can see that the merger was performed and the black hole was formed. And in the bottom panel, you have the unequal mass case, and even if we are here adopting a really low resolution, you can see that there is a kick in the black hole that it is somewhat expected from an unequal mass binary merger producing a black hole. Lorenzo is currently a PhD student at the RIT, the Rochester Institute of Technology, and is working in improving the treatment, the interpolation scheme for the generalized Lorentz gauge in the case of in the Spritz code. So when considering staggered vector potential. Those are preliminary results considering magnetic field. And you can see that in our first release of the code, we had some problem with the vector potential. You have here the norm of the magnetic field at the refinement boundaries. So there was some spurious magnetic field created. And so for such simulation, we could not avoid to use dissipation. Here is the actual status of Lorenzo work. So in the top panel is without dissipation, and in the bottom panel is with dissipation. So he actually changed the interpolation scheme adopted for vector potential and scalar potential. And you can see that the situation is considerably improved by this changing in the interpolation scheme, but still we need some dissipation for that. This is a work that is ongoing at the Center for Computational Relativity and Gravitation at the Rochester Institute of Technology, so stay tuned for more updates on that. And concerning instead the further development and future work, here I cite the talk by Jay Carinani, the lighting talk that Jay Carinani will hold later that day, about the improving of the conservative to primitive scheme adopted in Spritz. In particular, he cared about implementing the new Con2Prim scheme by Castaun et al. And he performed several tests, challenging tests for those scheme, for those new implementation. And another idea that Bruno told me was to test the handling of the magnetic field outside the neutron star. That could be of astrophysical relevance. And in addition, another idea is to improve the neutrino treatment. So switch from neutrino leakage, from the Zelmani leak to the same method adopted in whiskey THC, or to something else. The idea probably is to, at some point, go to the M1 treatment, but I cannot anticipate too much. So I don't know if I was too fast for the presentation, but this is all from my side.
Thank you so much, Federico. You do still have some time, so if you have questions, please go ahead and ask them. So we can maybe have a little bit of a discussion in the remaining time. Okay, so I don't see anything in the chat, but I actually had a question quite early on about the equations of state that you can look at. So are you restricted to these polytropes, or can you be more flexible? In particular, if people are thinking about using nuclear equations of states now, so how much flexibility do you have in Spritz?
Yes, considering the nuclear equation of state, we are, I think, the most flexible possible, because we implemented the possibility to treat the tabulated equation of state that is in general not strictly a polytrope or a piecewise polytrope. So I think that the flexibility in this sense is the best possible up to now.
Okay, great, thank you. We also have a question in the chat now. What is staggered vector potential?
Okay, okay, let me share the screen again. I can explain that in details. The staggered vector potential. So as I said at the beginning, basically when you adopt a numerical scheme for an evolution, for a numerical method in general, you are considering a discretization of the space of the domain. Okay, so you consider some cells, some numerical cells. You can consider the variables located at the center of the cell. That is what historically probably the code were doing. Or you can consider the values of some variables staggered on the cell's edges or faces, okay? And staggered vector potential means that you reconstruct, you calculate the magnetic field from the evolved vector potential, okay? You consider the vector potential located at the edges of a cell face, okay? And you therefore are considering like a simple solenoid, okay? The resulting component of the magnetic field located at the center of the cell face, okay? Center of the cell, center of the cell, center of the edge, and sorry, center of the face, center of the edge, okay, here, and center of the cell, that is this one. And adopting such a treatment, we notice that you can obtain some more accurate results for the magnetic field evolution.
Okay, very good. So one more question in the chat. For the small differences in your comparison with GRMHD, I guess GR hydro, is that physical or does it converge away?
Well, good question. I don't, unfortunately, I don't have an answer because we performed the simulation up to 6 milliseconds. But the entity, so the entity of those differences are really smaller, really comparable, the two results. So it could be also a matter of some differences in the code, okay? That but up to 6 milliseconds, it is not concerning at all.